Okay, so welcome everyone to today's IAMP 1 Volt Mathematical Physics Seminar. It's a great pleasure to introduce today's speaker, Jacob Shapiro from Princeton University. And Jacob will tell us about continuum and strongly disordered topological insulators. And let me say that, as usual, the seminar will be recorded and made available on YouTube. Jacob, we're very much looking forward to your talk.
Thank you, Marcello, and all the organizers for the invitation to speak here. I'm very happy for the opportunity. So indeed, I will talk about two problems that were published recently about continuum versus discrete and strongly disordered topological insulators. You can see my plan here. First, I'll maybe to the detriment of experts, but still I'll give a very basic introduction to topological insulators. I'll run through some examples and also talk about my basic vehicle to get results, which is Fredholm index theory. And essentially, really, the main message of this talk, as I intended, is to communicate just how powerful this tool is. Then I will explain about the continuum versus discrete problem, and which I did with Michael Weinstein. And lastly, I will talk about the strongly disordered time reversal invariant problem, the so-called Foucault-Milly system that I did together with Jeff Schenker and Alex Bols. All right. So first, I'll just try to give a very brief introduction into what topological insulators are. I see that there are many people here who know this way better, but still, since this is a large forum, I'll spend some time doing that. So what is the setting here? We're interested in studying non-interacting electrons in solids. So there are electrons, so there is the Fermi exclusion principle, but otherwise we don't care about interactions. And we do so quantum mechanically. So we take a Hilbert space, which is going to be L2 of some X, the configuration space, and then we tensor with Cn. So here X is supposed to be a real space, and this is supposed to be some internal degrees of freedom, like spin or isospin, whatever have you. And the X configuration space that I have in mind is one of the following options. It could be RD if we have continuum bulk systems. It could be ZD if we have discrete bulk systems. Or it could be RD-1 times 0 infinity if you have continuum half-infinite edge systems, or ZD-1 if you have discrete edge. And the distinction here between infinite and half-infinite systems turns out to be important. It's one of the main themes in this in topological insulators. Having said that, I'll actually spend most of the time talking about bulk systems. All right. So now that's the Hilbert space, but the solid itself is specified by a choice of a Hamiltonian. So it's some self-adjoint operator on the Hilbert space. But it should obey in order for the systems in order for the questions that we ask to have interesting answers, it should better have two further properties. One of them is that it is an insulator, and that is the name in the title. So very intuitively speaking, it should not conduct DC current. although mathematically speaking, this remains vague. So there are various ways to put this into the operator. One way is to say that it has a spectral gap. So you would say that there is some interval delta such that the spectrum of your Hamiltonian, it's a self-adjoint operator, so it has a spectrum on the real line, does not intersect this interval. But saying that alone is still not so interesting because many operators of interest anyway do not have spectrum throughout the real line. So actually the situation that is more interesting is that the spectrum of the Hamiltonian has at least two components. I'm not specifying what is the type of spectrum, just saying that it has at least two connected components. And this delta is any interval that has spectrum below and above. If the spectrum only below, only above, then it turns out to be not so interesting. This is what's called a spectral gap or spectrally gap insulator. There's also more generalized ways to define this notion. They go under the name of a mobility gap. There are some people in the audience who are experts in that. But for now, let me just remain vague and say that the spectral gap condition is, let's say, the convenient one, but not the most interesting one. And the second condition that you should also make in order to get interesting answers for your questions is that of locality. So it's the statement that H corresponds to a physical system. Perhaps that should have been the first condition. So that really should mean that its action is local. And one way to say that is to assume for a moment that H has an integral kernel. So I can speak about H xy between 2 points in my configuration space. That's going to be an n by n matrix as I set it up. And I ask that it decays in the distance, let's say exponentially, although the particular rate is not extremely important. It should just be fast. All right. And if H has no integral kernel, then maybe there are other ways to specify this, but this will certainly do for now. Okay, so that's the kind of systems that we're interested in, operators on L2 of X that have a gap, some kind of gap, probably spectral gap, and do not have a very long range action. Okay, and so what is the idea for topological insulators? Okay, so the idea very simply is just to do algebraic topology on this space of solids, as it were, that are specified by what I chose. So that means Hamiltonian, which obeys 1 and 2, and furthermore with the configuration space and delta, and I haven't said what this is, but I keep it still for now, maybe symmetry class fixed. So I fix my configuration space, the gap, and possibly the symmetry class. and I want to study the classes of such operators. So I call this space of solids. Maybe I call it A, X, delta, maybe S for the symmetry. And in order to do algebraic topology on this space, it better have some topology, which I also haven't specified. But in some situations, there is a natural one. And so the idea is really that you calculate pi0, the set of path-connected components of this space. And maybe you can prove that it is isomorphic to Z or to Z2, or maybe it is null homotopic. And furthermore, maybe you can exhibit the isomorphism. And that isomorphism is actually the invariant that goes from this space into this discrete set. So really the idea is to be able to maybe find this isomorphism. First, you have to define the topology on this space, and then you'll want to very explicitly calculate this invariant, which is constant on path-connected components. So I think that rarely topological insulators are introduced in this way. And the main reason is because we actually cannot do it, or at least I cannot do it. Especially not in this strongly disordered regime. This is really just a schematic to sort of at least orient myself into the logic of why we do what we do. Having said that, most of what I will talk about will really only concentrate on exhibiting one such function, which is the invariant, the index, and studying various properties of it. I will definitely not at all define topologies on this space or prove that that pi0 is anything. I really only put it here for schematic reason. Okay, so this was really rather abstract. So let me now get down and become a bit more concrete. Unless there are questions, by the way, I very much welcome interruptions. Okay. So to become a bit more concrete, let's look a bit more into the physics. So we look at the physics picture, and so here I specify to d equal to 2, which will actually be the entirety of the talk, and I will for now have no symmetries. And so let me talk about what is called the integer quantum Hall effect, which I guess was born in 1979. It was discovered by von Klitzing. So in this integer quantum Hall effect, you have a two-dimensional system. Indeed, we specify to d equal to 2. And you have electrons that are moving in a homogeneous perpendicular magnetic field. So if you have this setup, then initially the electrons just move in closed circles. But if you apply a vertical potential, let's say V2, then these circles will change into a drift motion, appealing to your classical intuition. And so you will actually measure current in the one direction. This phenomenon was already studied by Hall many years ago, way before von Klitzing. and Hall then defined a Hall conductivity, which is really just a ratio of this current by the voltage. And he defined it classically. Okay, however, von Klitzing, when he ran the experiment with gallium arsenide at very low temperatures, at very strong magnetic fields, what he discovered was that, I mean, from this relation over here, you expect that as you have more electrons or higher electron density, and then the current is higher, and then you just see more conductivity, but so you would expect such a linear picture, but what he discovered was a picture of plateaus, of steps, and really, in order to understand these plateaus, one needs quantum mechanics. So in quantum mechanics, there is actually a tool to calculate how the system responds to the application of voltage. It's under the general name of linear response theory, or Kubo formula. And when you make this calculation, then you actually can see that one way to write this, and now this really depends on the operator and maybe also on the gap that you choose, because you will need a gap, is that this is equal to something like some constant times the trace of P, and then there is some double commutator of lambda1 P and lambda2 P. So now I have to explain what all these symbols mean. So first of all, P is going to be the spectral projection onto all states below the gap. So you imagine that you have the spectrum of the Hamiltonian, and maybe there's some states here, but the gap is outside of the spectrum, and mu is called Fermi energy. It's any point outside of the spectrum and within this delta. Okay, and what are these lambda1 and lambda2? So you have a two-dimensional space, and it has 1 and 2 axes. So lambda1 projects onto this right-hand side of space, and lambda2 projects onto the upper half of space. So this is lambda1, and this is lambda2. Okay, so it turns out these are all highly non-trivial statements. Many of the people that I see in the audience contributed crucially to what I'm about to say. I don't even try to mention all the names, but I'll be happy to do so in the end. Anyway, it turns out that when the projection projects onto mu in the gap, then this object over here is indeed trace class, and so you can take its trace, and the trace happens to coincide with a linear approximation for this Hall conductivity. So that's a quantum mechanical way in order to calculate this, what is at first defined as a classical quantity. And as I write the formula over here, it's still not entirely clear why there should be these plateaus and not a straight line. In order to understand that, one still needed to work a little bit. So there came the work of TK and N, which, if I'm not mistaken, was in '82, and then of Avron, Zeiler, and Simon, which I think was either in '82 or '83. Perhaps I can be corrected about this. At any rate, this group of people first understood that this is an integer, but they still didn't understand that it's a topological object. And however, Avon, Zeiler, and Simon did connect it to a homotopy invariant. And once you understand that, then first of all, it is clear why it has to take these integer values, which it does in appropriate units. Furthermore, why there might be a possibility for plateaus, which really have to do with the fact that because this object has a topological interpretation, then you could deform the system in certain ways and still it doesn't move. And here, actually, how you deform it is you move within the localized spectrum, and well, I mean, it is at least intuitive why adding more and more localized states, filling up the system with more localized states would not change the conductivity. All right, so that's the more concrete picture that one has in mind to go either before or after this abstract mathematical introduction. And I would like to also give really concrete examples of models where one actually sees something interesting. Just to sort of have an intuition for what it is that you actually study. I mean, at this point, no Hamiltonian is even exhibited. It's not clear exactly what you should take. So here are a few examples, and the first one is relatively modern. So for this example, you take discrete space. You take 2 degrees of freedom on each lattice site. And so out of this, you get the Hilbert space, okay, what I said before. And take some parameter A, which is any real number. And then one defines the so-called half Bhz model. It's for Bernweg, Hughes, and Zhang. Actually, the full Bhz model is also interesting in our context, but let me first speak about the half one. So in order to define it, I define a basic operator, which is the right shift in the jth direction. So I have 2 directions in the system, the vertical and horizontal. And so j could be equal to 1 or 2. And what this operator does is really it just it moves you to the right by 1 unit, like so. So this is the standard unit vector, and x would be any point in Z2, and psi would be any vector in your Hilbert space. All right. So now I have these 2 shift operators, and I can define the Hamiltonian, and it would be given as the following combination. So I have to define it as on this tensor product. So I define it as such. It's a shift in the 1 direction, and then I'll have the following spin operation. Then I have shift in the 2 direction, and I'll have a corresponding shift also in spin. And this is not itself adjoint, so I had Hermitian conjugate to that. And then furthermore, I add to that the parameter A, and then identity in space, and sigma free in a spin space. So here by sigma, I mean the poly spin matrices. So it turns out that if A is not equal to 2, then there is a gap about 0, this model in principle will have two bands. The easiest way to see this is to recognize that this model is translation invariant. So you can actually do a Fourier series or a Bloch decomposition, if you will, and study its spectrum. It just so turns out that when A is not equal to 2, then there is a gap about 0. So probably you should take there to be some epsilon bar about 0. And it is a calculation that I will not do right now, but still it is a calculation that the whole conductivity associated with this gap and with this Hamiltonian turns out to be either plus minus 1, depending on whether A is in plus minus of 0, 2, or it is 0 if A is in absolute value beyond 2. So that's one very concrete model where you actually see this non-zero invariant. So in case it wasn't clear, this sigma whole is meant to be exactly this invariant. So I haven't said that. Another example that is less recent and I hope more familiar is in the continuum, and it involves the Landau Hamiltonian. So this actually has no solid in it, or no structure of atoms, as it were. You just put the most basic system that you study in undergraduate quantum mechanics, which is this one. So here P is the momentum operator, the gradient, and X is the position operator in the continuum. What I mean by this is that I will make a 90-degree rotation of the position. And that's one way to implement the symmetric gauge for a homogeneous magnetic field of strength B. Okay, and so this is a classical problem, and you can calculate that the spectrum of this operator is B times 2n plus 1. So it's just an infinite sequence of points that you have on the real line. Each point is actually infinitely degenerate, and it starts at B. Okay, it just so turns out, and again, this is actually a calculation that I will return to in a minute, but let me not say exactly why right now. But so if you put the gap somewhere in between these points, and you want to calculate the whole conductivity, then it turns out that the minus of it is exactly the number of points in the spectrum below. So it is each such level is called the Landau level, and the whole conductivity is exactly the number of Landau levels below mu. It just so turns out. Okay, so these are two non-trivial examples in the continuum and in the discrete space. And now I want to kind of introduce one of my main tools. So it starts, I guess, with a theorem by Belisard, Van Elst, and Schulz-Baldes. I believe the first time this appeared was in 1994. So the theorem says the following. It says it's what they call an index theorem. So it says that the whole conductivity of Hamiltonian in a certain gap is going to be given by the index, I'll say in a minute what this is, of an operator PUP plus P perp. So P perp means just 1 minus P, and that is manifestly an integer. Okay, so let me explain what these symbols are. So P is, as before, is a projection onto all states below this gap, assuming that H indeed has this gap delta. And U is a unitary operator, which is diagonal in the position basis, that essentially gives you the polar part of the position operator. So perhaps a complicated way, but still one way to write it is as such. But really, it just essentially means this. So this U is fixed. It's not going to depend on the Hamiltonian, and the only input from the Hamiltonian sits inside of P. So they prove that this trace formula that really is not clear why it is an integer, why it is topological. I mean, in certain situations it is possible, as I said already in the 80s, it was possible to understand it topologically, but anyway, they gave it the interpretation as the index. So what is this index? And again, I apologize to those people who are bored by this, but I prefer not to assume that that this is general knowledge. So an operator, a bounded operator, and this is a bounded operator, right? Because it's just a combination of projections and unitaries. Bounded operator on Hilbert space is Fredholm if it obeys the following properties. So it's kernel and the kernel of F star are both finite dimensional, and furthermore the range of F better be closed. If you have these properties, then you are allowed to call this a Fredholm operator, in which case the index of it is defined as the difference of these two dimensions. And so from this definition, it's clear that it is indeed an integer. But furthermore, and that's really the main tool of what I want to use, is that the index of F plus G is equal to the index of F if either G is sufficiently small, and when I say sufficiently small, of course, it depends on F, or G is compact. If you have either one of these two properties, then the index is stable under these perturbations, and that's really the main tool that I think can lead to a lot of results in a relatively soft way. And indeed, that's essentially all I will use. So here are a few examples just to orient you. So anything that is invertible is obviously of index 0 because it has no kernel, it has no co-kernel. I haven't said, but when the range is closed, then this is also equal to the dimension of the co-kernel of F. 0 is obviously not Fredholm if you're in an infinite dimensional space. And if you take the index of a M by N matrix, then the index is just M minus N by rank nullity. So it kind of doesn't depend at all on the matrix, it's just accounting of the dimensions. And finally, perhaps a interesting example is if R is a right shift on the half space L2 of n, not Z, which really means this. So so it should be, I think, a plus, oh no, a minus. Then it has no kernel, but it has a co-kernel because R star is the left shift, and it would kill the first site. So the index of this is actually -1. All right. And actually, with this example, which I hope makes sense, it is possible to explain why the whole conductivity of each Landau level is exactly equal to -1. I still do it in an intuitive way, but I think it's pretty closely along the lines of the Avon-Zeiler-Simon paper from '94. So they were the ones who explained this, I believe, in this way. So let's take P as a projection onto just one Landau level. And actually, from the way that this is defined, then it's clear that it will have an additive property. So it's enough to understand projection to just one level. And if you do that, then you look at U, which is this e to the I argument of the position operator. And if you think what it is for a moment, then this is really just a right shift in angular momentum. Right, that's essentially what it is doing. If you now restrict it to just one Landau level by doing this combination, which is exactly what we had in the Belisard-Van Elst-Schulz-Barders theorem, then you see that essentially what you're calculating is the index of the right shift operator, but restricted to one Landau level. And the right shift is in angular momentum. And if you have ever played with if you've ever played with the Landau Hamiltonian, then you know that actually it has only positive angular momentum. So really, this is kind of like the right shift on L2 of n. And so from this, well, still intuitive explanation, it should be clear that this index is exactly -1. And if you want the rigorous explanation, then you can find it in this paper by Avon-Zeiler-Simon. So the idea for this talk is really to convince you that by using relatively soft properties, namely these two properties of Fredholm indices, if you're able to do what Belisard, Van Elst, and Schulz-Barders did, namely to re-express your physical quantities or your invariants as indices, then you can get relatively far. In the interest of time, I will go straight ahead to the first result that was obtained using these tools. So this was as I said, a result that was obtained together with Michael Weinstein, and by now it is a paper that will appear in the Advances in Mathematics. So first, just the question in general, which is if you have two models, H in the continuum on L2 of RD, and you have a discrete model on L2 of ZD, let's say there are two bulk models, and they're not just any two random models, but they are related to each other in the sense that maybe H discrete maybe captures or describes the effective evolution of the continuum maybe at low energies. So I will specify in a minute exactly what I mean by this statement, but in a sense, the discrete Hamiltonian is derived out of the continuum one. Then you can ask if both are topologically non-trivial, what is the relationship between the indices? Or invariants? Okay, so in this generality, we don't answer the question, but we specify to the integer quantum Hall effect, which I've explained above. So that means that we take d equal to 2. And furthermore, we don't study just any model of the integer quantum Hall effect, but we study very particular, what we call a tight binding models. So we want to model the integer quantum Hall effect, so we better have a magnetic field. So we start with a continuum space on L2 of R2, and our continuum Hamiltonian, which I just call H, not H continuum, is given by this quantity. Actually, the beginning is just like the lambda Hamiltonian, but the magnetic field I now call a lambda. And then this very same lambda I take as the strength of a potential, which is the sum of translates on Z2 of a one atom potential. So this one atom potential would maybe look like so. It would maybe be smooth and have compact support. Maybe its support radius would be A, something that is much smaller than 1. And here it takes the minimum at -1, and here is 0. So we take this potential and we put it along the sides of a lattice, let's say Z2. Actually, Z2 is not extremely important. You can take any other lattice. I mean, of course, there are some conditions, but there's a general class of lattices that you can take for that. And another interesting object here is the one atom Hamiltonian. So it's exactly the same thing. I will just copy and paste it. But I just put one potential at the origin. So it's just the system with one atom in it. And when you study its spectrum, then you realize that because this has a negative potential, then there will be some bound states in this potential, maybe that will look like this. Let's say E0, E1, and so on. And of course, I need some conditions on V in order to run my theorem. But let me not tell you what is all the fine print and instead get to the interesting results. So this is the one atom Hamiltonian. So I take phi to be the ground state of the one atom Hamiltonian, which has energy E0. It has actually Gaussian decay at infinity in a manner very similar to how you derive Agmon estimates for non-magnetic operators. Okay, now when you study the spectrum of the full Hamiltonian, then you see that each such level will spread, and that's because of tunneling to nearby atoms. Actually, the width here is related to the tunneling amplitude to the nearest neighbor, and as you tunnel far and far away, you actually spread less. So this width is about exponential order in lambda, but it's still around E0, and this is still around E1. So, for example, one fine print that I haven't said, but now I'm saying, is that you want E0 and E1 of the one atom Hamiltonian. They may even depend on lambda, but you don't want them to collapse so that suddenly these two bands will touch. So that would be a natural requirement. Okay, and now you define the magnetic translates of your one atom ground state as follows. So you take the ordinary translate and you add this magnetic translation, which is necessary because this is a magnetic system. These magnetic translations are actually what commutes with the magnetic kinetic energy. So if you look at this set as n ranges in Z2, then it is, as lambda goes to infinity, this is an approximate eigenbasis for the states in the first band. It's a non-trivial statement, but it is true. However, it is not orthonormal. And the reason is that even though it has this Gaussian decay, it still has some overlap, so it will not be even orthogonal. And so in order to deal with that, you can define a Gramian, that's standard procedure in linear algebra, just to orthonormalize the basis. So this is an operator on L2 of Z2. And this operator is quite interesting. It's basically the identity operator plus corrections that are exponentially decaying, and you can prove various things about it. All these things are really consequences of the Gaussian decay of the one atom ground state. So, for example, you can prove that in operator norm, it's as close as you want to the identity operator. You can prove that it has also Gaussian decay, and so on and so forth. And so because of that, I can look at its, I mean, for example, this already tells you that it's a positive operator, which you actually already knew because of linear independence. So anyway, so I can define the inverse square root of it, and together with the inverse square root, which also inherits these decay properties, I can define an orthonormalized basis, phi n tilde, which is really just conjugated by m. And now you can verify that the tilde basis is a orthonormal, and it spans subspace of this essentially the first band over here. But because it is orthonormal, then now I can define a partial isometry, I call it J, from big L2 to little L2, that will just send any such basis vector into the basis vector in little L2 of Z2, and otherwise extend linearly. And by zero outside of this subspace. Okay, so I had to spend quite a bit of time to set up this language, but it was necessary to state this theorem. Which says exactly in what way do I mean that there is an effective discrete Hamiltonian that captures the dynamics. So the theorem says the following, that there is H tight binding on little L2, which is independent of lambda. And actually, it turns out that this is just the Harper model if you really take Z2. And there is some parameter rho of lambda for which you have bounds, exponential bounds, let's say in like so, such that you get a normal resolvent convergence. So for every Z outside the spectrum of this tight binding Hamiltonian, there exists some sufficiently large coupling constant so that for all coupling constants above it, you have the following. You take your continuum operator, you shift it by E0 and you scale it. You look at its resolvent at Z. And then you compare that with the tight binding operator that is brought to the continuum. And you also need that resolvent, and that thing is exponentially decaying in lambda. So I don't want to say a lot about this theorem. I want to go directly to one of its consequences, which was the agenda of my talk, which is that indeed, I mean, the normal resolvent convergence in a sense implies something about the dynamics of these two models agreeing. And really, you only get information about what's happening in the first band. But once you know something about the dynamics, and in sort of in a very soft way, right? I mean, there's nothing about matrix elements or integral kernels. Then you can actually derive a result about the Hall conductivity. And the main reason why we're able to do so without, being forced to ask about decay rate of this object or how it behaves, how its integral kernel behaves, is exactly because of the soft but however extremely strong properties of the index formula. So the theorem says that if the tight binding operator has the gap delta, then the shifted continuum operator has a gap rho delta, and the invariants associated with both gaps agree. The respective invariants associated with both gaps agree. I barely have any time left, but I just want to at least start the proof of this theorem. Then that's kind of why I set up everything. And they agree, of course, they agree if lambda is sufficiently large. So just the beginning, why this is true. So I have the tight binding projection, Fermi projection, which is by definition projection onto all states below this mu, where I had the gap. And because there is a gap, then I can write it as a Ritz projection. And I can do the same thing for the full continuum projection, which is defined as this. And so the previous theorem implies that in norm I have P minus J star P tight binding J converging to 0 as lambda converges to infinity, just by writing it this way and assuming that there is a spectral gap. So looking at the definitions of both the continuum, which is this index in big L2, and the tight binding index in little L2, you can maybe start to imagine why the theorem should be true, because as we saw, the index is stable under norm continuous perturbations. The reason why this theorem is perhaps not entirely trivial is because U tight binding, if I bring this to the continuum, is actually not equal to U. In fact, this guy is not even diagonal. And this has to do with the fact that that my basis is not just the delta basis, right? It's not the basis of delta functions. If it were, then life would be very easy. So I have to take care of that, and that's why this theorem is not entirely trivial, and not just a corollary of the previous theorem. So I think I will end with that, and maybe just say that in addition to this theorem that works on R2 and Z2, you can also prove an analogous theorem at the edge, where you work with the half space configuration. Actually, the proof becomes way more complicated because the edge states fill up this gap. So you cannot use such nice formulas, but still there is a way to get ahead. And really the main reason why is due to the very powerful properties of the index formulation, which also exists for half-infinite edge systems. So with that, I will finish. I just go to the first slide. To summarize, I told you a little bit about topological insulators. I gave some examples. I hope I convinced you of the power of this approach, at least with this problem of continuum versus discrete topological insulators. Unfortunately, I didn't get to speak about the time reversal invariant strongly disordered problem, but it is another example of, I think, where this approach is quite powerful. So thank you very much.
Thank you very much, Jacob, for your very nice talk. Are there questions or comments from the audience? So I think I have one, a very naive one. So about the index for the continuum model, are there results that allow to relate that to Kubo formula?
I'm not sure about it. Perhaps not. I don't think there are there is a paper by Hermann Schulz-Waldes and Johannes Kellendonk that exactly study this formula and prove that it makes sense in the continuum.
Mm-hmm.
But I'm not exactly sure if they have a full derivation that it actually is equal to the double commutator formula in the continuum.
Mm-hmm.
Perhaps for them it is only enough to just show that this index, makes sense.
Yeah. Mm-hmm.
If you don't want to relate it to the double commutator formula, then you can relate it to the index of pair of projections, which is another sort of at least heuristic argument for why this is the whole conductance, and that is done by Avron Zeiler Simon.
Mm-hmm. Yeah. Thank you. I see a question from Gianmichele.
Yes, thank you. About the theorem with Michael Weinstein you presented. So you reduce the computation of the index of the full problem to that of the tight binding approximation. Can it be then computed from there further? I mean, depending on details of that model?
Well, it would actually be exactly the Harper Hamiltonian. So if you know how to calculate the Chern number for Hamiltonian, then you can continue.
Okay, thank you. I didn't realize that this was the result you end up with. It's not, it must have something to do with the scaling of your B field or something, because at first it looks like an atomic limit, the limit you are treating, but apparently it is not quite, because in an atomic limit, the insulator would be trivial. Exactly.
So, I mean, this really has to do with the fact that I didn't emphasize this enough, but I take this constant and this constant to be exactly this particular scaling, and it is exactly that which guarantees that you do not converge to the atomic limit. Otherwise, actually, there is a paper by Belisard and Nakamura that says that, that the Chern number will be trivial.
Yeah, thank you. And then if I may, just another question. You mentioned the half Bhz model. What is the full one?
So the full one is actually, you explained to me how to take a Chern insulator and turn it into a Foucault-Milli model by taking the Chern insulator and then doubling it with the time reversed one on the other copy. Okay. So you can do that and you can get a full Bhz model. You can even add off-diagonal, what they call, I think, Rashba coupling. But I think it's not even necessary for what they call Bhz model. And that would be a Foucault-Milli non-trivial. I think that was the first one they came up with, and then they realized it's actually giving you a nice model for Chern insulator.
Thank you.
Other questions?
May I ask a question?
Go ahead, Jan.
What about fractional Hall effect? Can you modify these models so that they give fractional things?
So actually, excellent question, because everything I said is only for a single particle Hilbert space non-interacting systems, and I think it is quite widely believed that the only way to model fractional quantum Hall effect is using interacting many-body Hamiltonians. And there has been some very impressive progress recently, also by people in the audience, about the fractional quantum Hall effect. And I think it could be very interesting, although I don't think it is possible yet, to also phrase those many-body formulas for the Hall conductivity as an index already in infinite volume. As far as I know, this is not yet done, and as soon as you're in finite volume, you shouldn't really talk about indices of operators, but before. But when you're in the infinite volume limit, then there's some technical problems with defining the many-body Hamiltonian. So these are kind of two contrasting challenges.
Are there other questions or comments?
Does it mean that you can define non-integer indices? Or
Yeah, so I would refer you, for example, to the work of Bachmann, Bols, Frass, and Drock. It's a series of papers that appeared recently, where I think one consequence of these results is that indeed they can recover still in finite volume that there is a formula for some index that is rational. It's some P over Q, and there are some corrections that are smaller than any power in the volume of the system, something like that.
Further comments?
I have a short question.
Yes, Massimo, go ahead.
So thanks, Jacob, for the nice talk. So regarding the Gianmichele's question, the atomic limit, I mean, is it true that if you consider the full spectral island that you consider, then the Chern number, the total Chern number you get is 0, right?
That's absolutely correct.
Okay, so then it's only in some subspace that you...
That's absolutely correct. It's a subtle observation. Thank you for that. So the imagined situation is not that you take projection onto this entire thing, because indeed that thing, if the H-tight binding captures all of that, then it is all of its spectrum. And when you take the projection onto the entire spectrum, it's just the identity operator and it has trivial Chern number. But the idea is that the open microscopic gaps inside of this, and you actually project only onto a subset of them.
Okay. And can you do this kind of tight binding reduction if you consider a non-trivial spectral island maybe somewhere in the spectrum?
What is technically necessary is not whether this is trivial or not trivial, but whether you have a gap here of order 1, yes or no. That's what's really crucial here. And I think that there might be some obstructions to this exactly if it's non-trivial. I think
Okay.
maybe you have results to this direction that would not be possible.
I mean, the Chern, yeah, but it's not, I mean, the Chern number will not be 0, but then one might still construct some tight binding.
Yeah, I think what could be very interesting and what we've been really unable to do so far is, for example, to do a tight binding scheme that would capture 2 bands and then get a 2x2 model. But because of the asymptotic way in which this is set up, we're just not sure exactly how to do this.
Okay, thanks.
Thank you. Is there any other question? It doesn't seem to be the case, so thank you very much.
I think Michael raised his hand.
Oh, is there a hand raised? Or...
Michael?
Well, yeah,
Go ahead.
I wondered, you mentioned also the situation where you do not have a spectral gap, but there is a mobility gap. And in case of a mobility gap, there's a characteristic length, that of sufficient, that of decay, which gives the range of the decay. Do you expect an extension of your theorem going, relating discretized bond systems to continuum models under some conditions of correspondence of this localization length?
So I have 2 things to say about it. First is that I mean, no rigorous statement, but just an intuitive gut feeling is that in this business, the exact rate of decay of exponential decay is actually not very important. Any rate of exponential decay will do. Actually, you just kind of need summable decay into dimensions to have well-defined formulas. But relating to the other thing that you said, whether you could do something for continuum operators that have disorder, and furthermore, where this area over here is full with localized states, exactly as in the mobility gap regime. I think that's a problem of considerable analytic difficulty that we've not faced yet, but would be very interesting.
Thank you.
Thank you. Is there any other question? Okay, so it doesn't seem to be the case. So let's thank Jacob again for this very nice talk.
Thank you.